I'll be talking about the quantum unpredictability entropy in this talk. In this talk, I'll mostly focus on CQ states, which is the results in the first paper, but I'll mention from the top, there's already a follow-up paper where we extend all of these results from this paper to the fully quantum setting. Let's start by recalling an operational interpretation of the conditional mean entropy that is relevant in the CQ case. I have some random variable that I want to keep secret, and I fear that some information that might even be quantum leaked about it. The conditional mean entropy can be defined by the negative log of the best guessing probability using any strategy, any POVM at all. In this work, what we do is we look at a restricted class of guessing strategies where the same adversary is restricted to only use S gates. And S is a parameter for the complexity that the adversary can use, the computational power that the adversary has. Why is this interesting? Real devices in the real world, we don't have unlimited time, we don't have unlimited gates, coherence, so on. We know that some tasks are impossible. For any bounded time, we know there will be tasks that we cannot achieve with any reasonable probability in this time. And specifically for this context of cryptography, we often assume cryptographic hardness. And if we have a function that is invertible but is computationally hard to invert, then the mean entropy, the conditional mean entropy here will obviously be 0 because f has an inverse, but we want an entropy measure that will show that will agree with the fact that the probability of actually guessing X from this side information will be very low. Some more motivation is that the classical theory is very rich with a lot of uses and a variety of definitions for computational entropies. There's Hill entropy based on indistinguishability from true mean entropy sources, unpredictability entropy, which I basically described, Yau entropy on incompressibility of random sources. There are many known properties that these entropies have, and they're very useful in classical cryptography. In the quantum setting, up till recently, there was very little work. There was a paper presented here in QCrypt in 2017 about quantum Hill entropy. This work is about quantum unpredictability entropy. And there's recent interest in complexity-constrained thermodynamics. But the field is still very open, and there's a lot of opportunities to try to extend results from the classical world and from quantum information theory at the same time to quantum computational setting. Let's jump to the fully smooth computational unpredictability entropy definition. We say that we have a smooth epsilon s unpredictability entropy at least k if there is another state that is close to the state in purified distance, so in information-theoretic distance, such that any circuit of size modes S cannot guess it with very good probability, with probability more than 2 to the minus k. So we allow for smoothing, but the smoothing is similar to the information-theoretic mean entropy and not computational smoothing. This is important for some of the properties that we need. Like I said, we're trying to generalize the conditional mean entropy. So first of all, we show that there is a gap. There are distributions that have a gap. If we're going to give up the information theoretical security, we should at least gain something for it. It's actually always lower bounded by the smooth mean entropy for the same epsilon on the same joint state. If we allow the computational power to be unbounded, we recover the smooth mean entropy. And it behaves nicely as entropy in general. It has a doesn't of processing inequality up to some caveats that the data processing channel is doing some processing for us. So we need to account for it in the gate budget. The main thing we prove in this work regarding these entropies is they have a leakage chain rule. They behave as expected. This is a simple chain rule to show for mean entropy, but in this setting, it's not trivial. In fact, for the Hill entropy, this chain rule was one of the main barriers. It only holds for the case where X and B are both classical, and only the new leakage is quantum. This made it so that when you want to work with stuff like leakage resilient cryptography, you can only do bounded quantum storage model. And here we extend it actually in the follow-up work to the fully quantum setting where both X and B and C can all be quantum. And here we have 2 sign that corresponds to the possibility of super dense coding. We can, if we leak 2 more qubits, we can learn about the secret what's worth 4 bits of information. Let's see a very brief and simple proof, starting with the fully classical setting. If I have a joint distribution on X, Y, Z, I want to show that this unpredictability entropy is at least this. So I'm starting with a guessing circuit that has some probability. I'm starting with the best guessing circuit. And I want to build a new guessing circuit that doesn't use the additional leakage Z. What I'll do is maybe the easiest thing, I'll just put something random in there. And I know that there is at least one input that will be correct in this register, so the probability can only go down by 2 to the L. To illustrate it again, I have 2 registers. I lost one, so I just put something random here. So the gate budget is just what it's required to make fresh randomness here, fresh and independent randomness here. This is actually almost exactly the same proof in the fully quantum setting, except that the probability inequality is replaced by a pinching inequality that gives us exactly the 2 that we expect to get in the probability inequalities again. So we covered the quantum leakage chain rule. And yeah, this holds even in the fully quantum setting where it's a joint state for everything. I haven't defined what's the unpredictability entropy for fully quantum, but it works. One of the main reasons we care about mean entropy to begin with is the ability to extract nearly uniform randomness out of distribution with this entropy. The mean entropy characterize weak sources of randomness that are strong enough to be used to get nearly uniform randomness. In this case, we care about the situation where there's a public uniform seed and a source with conditional mean entropy, and we want to get out something that is close to uniform random on, of course, a little bit fewer bits. And it should be independent and secure even if the adversary knows the same side information and the seed in the end of the process. Like I said in the start, we start with something that can have no mean entropy at all as an input. So we can only hope that the output will be pseudo-random. For Hill entropy, this is actually very easy. And basically anything that works for smooth mean entropy will work automatically for Hill entropy by replacing the word purified distance with computational distance. Here we need something with a bit more structure. We want an efficient reduction of the following form. If the output can be distinguished efficiently from uniform randomness, meaning the extractor didn't output something that's pseudo-random, we want to be able to efficiently predict the input, to make another mechanism that will guess the input. Some known results about extractors that are secure against quantum side informations use inefficient predictors. So even known results like the fact that any extractor of a single bit is secure against quantum side information with basically the same parameters do not hold in the unpredictability entropy. Luckily, the Goldreich-Levin inner product extractor does work. We can actually create a guessing circuit that is efficient. Note that the seed is public, and we can start with something that didn't have any mean entropy to begin with, so we get pseudo-randomness just from the hardness of guessing X. And this is for a single bit, and we can get more bits without simply reusing the distribution in an IID fashion using Trevisen's extractor method. Trevisen's extractors that are known to be secure against quantum side information, and they're secure in this context too. Okay, to summarize, we introduced the unpredictability entropy, which generalized the mean entropy. We proved the leakage chain rule that was true in the fully quantum setting. We showed that we can extract pseudo-randomness from it. And these are tools that are good to analyze leakage resilient cryptography in the case of quantum leakages from both classical and fully quantum protocols. There's a lot of work still that we plan to do in this direction in the future. We are looking for a computational purified distance. We need a specific property that the purified distance has. That is the extension property. If we get it, we can have the advantages of both Hill and unpredictability entropy at the same time. Looking at more extractors, going beyond extractors and just CQ states. Looking at the fully quantum protocols. More entropies, not just the mean entropy, the resi entropy, the dual entropy, conditional max entropy, and other computational entropies are also interesting to extend to the quantum setting. And with this, I thank you and welcome questions.
Thank you, Noah, for the nice talk. Other questions? Yes, over there.
Thank you for the very interesting talk. Is your extractor future-proof or everlasting security or not? So can it be broken a posteriori, or it must be broken during its operation?
The output of the extractor is as secure as the input was unpredictable. So it's a similar S parameter. If you started with something that's computationally hard to guess, we get something that is computationally hard to distinguish from uniform random. So it depends on the hardness of the input.
So it seems that it's not everlasting secure. And can we what do you think? Can we hope for everlasting security? So if Eve doesn't break the protocol during its operation, there is no chance, like
it's
in
not.
QKD.
It's not information theoretical security, so it's not. It's not going to be.
Let it be computationally secure, but when Eve must break in limited time, not in unlimited future time.
So again, what?
My question is whether we can hope on computational but everlasting security. When if Eve wants to break it, she must solve computationally problem during the operation of the system. A random number generator or maybe analogous QKD systems, not in only during this operation.
In this setup, no, but could be in a different setup.
Okay.
But what if we use these entropies? Then I don't think so. No.
Thank you.
Another question on the back there, and then afterwards.
Okay. So thanks for your talk, and can you go to page 16? Yeah, I'm a little bit confused by this because in your equations, so I'm a little bit confused because the L is the dimension of C, so it's independent of B. So I would expect it should be something related to the property of subsystem B. So is there any utility this understanding?
Okay, there's the typo here is that
Okay.
this should be B.
Okay.
Okay, sorry.
Okay.
The leakage should be C, and this. Thank you for catching that.
Okay.
No, sorry.
Yeah, and also how do you
This one
determine
should
the
be
TL? Yes.
B.
Okay.
B is the one that stays, and C is the one that is new, there or not there. Sorry, that's
Yeah. Okay.
typo.
Thanks for your clarification. And also, I want to know how do you determine the TL? The increase in the time parameter, the gate size parameter.
The T is the size of a circuit that is needed to create a maximally mixed state on this auxiliary system, on this new system.
Okay.
So it's not very big. If the system is size L, it's something that's efficient in L.
Yeah. Okay. Thanks for your answer.
And there was a last talk, a question on the back.
Hi, related to Anton's question as well, is there any version of leftover hashing lemma for this entropy, or like, is that question even make sense?
That is an open question that we're working on.
Okay, thanks.
So I don't know. I hope so.
Okay, so let's thank Noam again